Hi, this is 3D scan of a motorcycle engine wall cover that was made by a viewer from this channel, and he sent to me for doing the reverse engineering. His intention was to 3D print this wall cover using the nylon carbon fiber filament. This scan was made with the Refinement Mini 2 3D scanner, and in my previous video I have already inspect this scan and I found a lot of issue with the precision of the scan. With the low precision scan, it will take a longer time for me to reverse because I can't see clear corner and edges. I will also have a different dimension from the left side and the right side. So I asked him if he can send me a new scan with other 3D scanner that give better precision, but he couldn't find one, so he sent me his measurement using a vernier caliper, I suppose. But when I do a reverse engineering with a 3D scanner, I will only rely on the data from the 3D scanner. If I use mixed data from other measuring tools like the vernier caliper, for example, if I use his dimension that he sent to me to draw the base, the mounting face of the valve cover, yes, I can draw this with this dimension that he given, but when I start to draw the walls that is taller from the mounting face, it's not going to align because the scan data has a different dimension from the vernier caliper. So I recommend that if you want to do a 3D scan, you get a precise 3D scanner that will give you less trouble. You can use the data from the vernier caliper on a standalone dimension, for example, the hole diameter, but the location of the hole, you are going to need to use the data from the 3D scanner. So next I'm going to move this wall cover into the center. As you can see here that this side of the scan is bad. It has double wall. This is supposed to be just a single wall, but it has double walls. So I will mainly use the left side of the scan. I'm going to find a symmetrical line, and then I will draw just on the left side. I'm going to create a sketch on XY plane. I draw a 3-point arc to get the center line of the circles. So now I have this at the center line. Move to the second hole here. As you can see here that the scanner has a lower precision and the edge of the circle has a double wall. So I need to pick one of that to be a hole center. So this is I'm trying to point out that the precision of the 3D scanner is very important for reverse engineering. So we have two walls here. So I will pick this point to be the center of a circle. So if I draw a circle, so this outer wall is the false of the 3D scan. It will be much easier if you can get a high precision 3D scanner. I will draw the line here from this point to this point, and I draw a point here. Okay, so this is the center. So the center is to the left of the origin point. So I need to move this along the x-axis for 1 millimeter. I need to move the point cloud to the right for 1 millimeter. Wall cover, edit attach data, and I'm gonna offset x-axis -1. The point cloud should be in the center now. Okay, let's check if I draw an arc again, hole, right? And then I'm going to mirror it to the other side. Okay, it should match the hole on the right side. See here, it's just a little bit unmatched, but it should be good enough. What can I do, right? So I'm going to crop the right side. So I'm gonna use only this side of the point cloud for referencing, and then I mirror it to the right. Okay, before that, let's create a plane on the mounting flank. I'll pick one point. I choose this one, clear the plane. Okay, this will be the plane for creating the flank. You can see here that it has double wall in some places, so it's quite hard to see which line. Let's go to the step I took to model this part. Okay, first step, I start to trace the mounting face of the wall cover. See this purple line here. Okay, and then I extrude the base up to this point, and I make another extrusion for 3 millimeters, and then I use a chamfer command to chamfer this corner. I made another extrusion here for 1.5 millimeters because this wall corner here is taller than the front part. Then I make a chamfer here for the rear part because it's taller. Okay, and then I start to create two sketch by using the point cloud I showed before. Make two sketch here, and then I use a loft command to loft it. As you can see here, I don't create inner wall shape. I only use the outer wall because it's faster to model with just the outer wall, especially this part. And after I model all of the outer wall, I will use a shell command to create a inner wall. Okay, and then I extrude this part to this point, just the whole part. Then I add this part, make extrusion on this part, and extrusion on this part from here to here. And then I extrude this part. And then I use sweep command to create a sketch here, and use this rail to sweep cut this fillet corner. Okay, next I create this cylinder bump on the top of the cover. If you can notice here that this cylinder bump, it will add to the cover for increasing the stiffness. There are 3 of them, and it lay closer to the mounting hole because that's where the fixing points are. So there are one here and one here. So original designer add this cylinder to increase the stiffness of the shell. When you pre-tension with the torque wrench, it will distribute the force to the mounting face equally without any deformation. Okay, here's a second cylinder that I was add to the top of the cover. And I add these profiles to the wall. Then I create a plane with the 3 points for trimming this face. Okay, and then I start to rough the real part of the cover by using this sketch and this sketch with the 3D rails. So if your CAD software can do a 3D rails like a Fusion 360, you can also model this part. But in a Fusion 360, you can't import point cloud, so it would be more difficult for you to see. And this is like 2 million points. Your performance on your PC will be different. You can't orbit, zoom, pan quickly, so it will take longer time for you to model this part. Okay, here's a second loft. I use the edges here for reference to create each step of the loft. This is the second step, and there's edges here that I use to divide each step of the loft command. Okay, here's a loft number 3. Okay, and this is the final loft. I add a fillet here. As you can see that all the models that I made until this point, I want to cosmetic chamfer and fillet because it will be very difficult to do the shell command. The shell command, you need the shape to be in a basic shape. If you put a lot of fillet and chamfer, sometimes the shell command wouldn't be able to execute. Okay, here comes the most important part, the shell command. The shell command will remove the volume from the inside of the solid and build the wall thickness automatically. And you can choose which face to be open. I choose this face and the bottom face for opening, so it will create a shell automatically. But the shape that you build has to be simple. if you build the shape that is too complex, there are going to be an issue with the shell command. So in this case, I don't even have to trace the inner wall. It's going to be complicated if I trace the inner wall and extrude or loft it, because there's cylinders, there are extrusion of the box and cut everywhere. So there's also a sweep cut here. If you model together both outer wall and the inner wall, is going to take a long time. Okay, after shell command, I need to thicken the wall. So I choose thicken command to thicken each face manually for 0.6 millimeters. So I will have total wall thickness of 2.4 millimeters, which is 6 wall layer if I print this with a 0.4 millimeter nozzle. So after thicken all the walls, I can add more complicated part like extrusion of this hole, mounting point. If I do this before the shell command, it wouldn't be able to execute because this curve is quite difficult for the software to offset the wall. So I add this later. Okay, so I create an inset for the hole. And finally, this hole diameter 11.4. I use the data from the viewer that he sent to me, measuring with the vernier caliper, because the hole that I measure from the point cloud is 11.6 or 11.7, depends on the location of the hole. It's given different values. So it's about 0.3 millimeter larger than the vernier caliper. Okay, next I create a stiffener here, just a simple stiffener. So this part is also add complexity to the shell command, so I do it later. And I add a little bit of the fillet here to the wall at this point. Okay, and then I create a second mounting hole here on the top. Okay, so the left side is complete. I use the mirror command to mirror it to the other side. Okay, let's take a look at the possibility to print this with a nylon or PPS filament. So if I print with a nylon, it's oil and grease resistant. So for the wall cover, it should be compatible. And it starts to melt at 190 degrees Celsius. Heat deflection temperature is 110 degrees Celsius. Okay, let's take a look at the tensile strength in the XY. 66 on the Z-axis, 43 megapascal. So remember this number, 66 and 43. So I've done the stress analysis of this wall cover using nylon as a materials, and I apply load at the mounting face. The load that I apply, I converted from the pre-stress value of the M10 bolts. This wall cover will be mounted with the 3 M10 bolts. I use this mounting point as a fixed support, and then I apply the pre-stress force at the mounting face. So the way I calculate the pre-stress force is by using the torque on the screws. It's recommended that for tightening the wall cover, you use 7 Newton meter. For tensioning the bolts, 7 Newton meter per bolt will translate to 700 Newton. So the minimum force from the pre-tension of the bolt is 70 kilograms for each fixing point. Okay, and here is the analysis result. You can see the deformation. When you compress the wall cover, this edge will start to lift up. That's why the original designer, they add this cylinder to the top of the cover to increase the stiffness. See the movement? They are all there for a purpose. Even this stiffener, see here? This stiffener also preventing the cover from deflection. So you see why they add a thickness of the back here, because this will be the part where it's deformed the most. So when you are tightening your bolts, this is how it will move. This is exaggerate movement, and this will be the part that it will break. In the green area, you get the stress around 42 megapascal. 42 megapascal. So for the nylon without carbon fiber, it's very close. That's 43 without any safety factor. So after you pre-stress it, it might survive if you print this with the nylon without the carbon fiber. So let's check the displacement. If I check the displacement, this point will lift up almost 7 millimeters with the nylon. But that may not be true because in the actual usage, this mounting point is going to be compressed with the engine valve. So it shouldn't be able to go below this point, right? Because it's going to be attached to the engine valve. So this number could be lower. It is likely that this edge of the valve cover will lift up. I think the oil could be leaking if you use the nylon without the carbon fiber. Okay, let's check with the other filament option that we have. If you look at this table, you will exactly know what kind of filament that you want to pick. So we need something that is closest to the aluminum. Now we have a PPS, but a tensile strength is not much. I will choose PETCF. Yeah, I think PETCF 17 will be the best material for printing this. It has the highest stiffness and acceptable tensile strength. Yeah, I think so. The PPS wouldn't be suitable because the tensile strength is really low. 32 megapascal, it will not survive the bolt tensioning. PETCF, yeah, young modulus is 5481, 147 degrees Celsius. That's acceptable for the valve cover. PETCF, yep, I recommend that you can try with the PETCF and it should work. I don't have this available in my location. Okay, let's bring into the slicer. This time I use STL because I have tried with the step files. The slicer cannot fully open it because the part is quite complex and the slicer is not be able to open that. So I need to export as STL files. So here's the part. So if I want to print this with the ABS, let's change to white color. Can't see this. And I'm gonna align this in this orientation, 45 degrees approximately, because I want the pocket for the oil seal to be print perfectly. So I don't need support if I put in this orientation. The oil seal will not require the support to print. Let's go here, enable the support and slice it. I need 121 grams to print this. And it's 4 hours 15 minutes, almost 5 hours to print. So some of the part is not support here. So if I look at the oil seal, we have a 1, 2, 3, 4, 5. We have 5 layers of the wall. So it should be strong enough to hold the oil seal in there. The viewer also specified the width for the oil seal. It's 2 by 2 millimeters. Okay, let's change these materials to if I want to print with the PLA, because PLA can print with the side fan cooling, it should give a better printing with the overhang area. And for the PLA, I will print with the support interface using the PETG so that I can set the top C distance to 0. This will make it surface of the contact area of the support smooth as much as possible if I set it to 0, because PETG will not adhere to the PLA. But in fact we can't use it for a functional part. Okay, that's take 9 hours 54 minutes to print, but it should be print perfectly because of filament changing hours. So, and if I click on here, support critical region only, I could reduce some time in the trade-off for some part of the overhang may not print properly. So only critical part will be supported. So now the printing time is cut down to 4 hours 47 minutes. So it's faster. So I choose this one. I don't have much time. I choose to print, I will print with ABS, one with ABS and one with the PLA. and compare the result. Alright, let's send it to the printer. Okay, here's a print from the ABS filament. See, the outer shell look nice and clean, and on the inside it's perfect. And the part where it's going to be joined is perfectly print. It's going to be the oil seal pocket. So if I print in this orientation, the oil seal pocket can be printed without a support, and it comes out very nice and clean. The only issue is that on the side with the overhang, see here, this part has no support, and when it's trying to print, it's turned out not so good. And the part where it has a support is quite rough, but you can sand it. You can sand ABS and nylon, but nylon you have to put more effort for sanding. So this part has to be repaired. If I will print this with a nylon, it's going to be the same, because with the nylon you can't use the side cooling fans. So after this, I'll try to sand it, and I will repair it with a filler, paint it, and see how much improvement can it make on this side. And also make the print with the PLA just to see if there is any differences. So on the top is the PLA, bottom ABS. Yes, PLA prints overhang better because it can use part cooling fan and side cooling fans at the same time, but the overhang is still there. I can still see some overhang here. And I print this with the PETG interface for the support, so the flat part is smoother. This generation of the printer, ABS and PLA gives the same result. I can't even tell which one is PLA, which one is ABS. I mean, look at the layer lines, it's the same. This is a high-speed PLA, this one print with a high-speed ABS, but I can sand ABS, but with the PLA it's more difficult to sand. And paint. Okay, on the right is the result from sandblast texture paint, and on the left here is just the print with the PLA. The glossiness is about the same. And if you look from the far distance like this, you won't see any layer line from the print. But if you look closely, you're going to see the layer lines. But with the sandblast texture paint, there is no visible layer line anywhere. So this will look more like injection mold. So I use only one coating of the primer. It takes about 10 minutes of the curing time for each layer of the paint. I paint 3 layers, 1 primer, 2 top coat. So this part takes about 30 minutes to complete. I didn't apply a good filler here, so it doesn't come out very good for the filler application. So I think it's a good choice if you want to print the functional part without any other knowing that it's a 3D print. There's no layer line anywhere. See here? This one is smoother, of course, but you can see banding and layer line. This one is not slippery with the grip. It's quite rough. I think this texture paint is very good.